just my head. Welcome back, chemistry fans. What we're going to do today is we're going to talk about Unit 2, Topic 1. We're going to try and get you reacquainted with the states of matter and then some of the little terms that actually decide or that can describe what matter can be broken and classified into. So let me share my screen and we'll just get right into it. Okay, so I promise you that at some point in your science career, you have talked about different states of matter. And so none of this will be revolutionary to you, but some of it may add a few little details that we've got to talk about. So you are aware there are three states of matter. There's solid, liquid, and gas. But to AP up this topic, what they want you to emphasize is being able to draw these structures. They want you to be able to notice that solids, you represent them on the atomic scale as little spheres that are connected together, that they are only able to vibrate. The liquid, you'll notice there's a little bit more space, as well as the gas, even more space. They are both liquid and gas fluids, and so they are able to flow, be able to be poured. And you will notice that they have some similarities, the liquids and the gases, because they definitely have no shape. You can pour them into any kind of a container you want. However, only the gas can be squished. It can be compressed. It doesn't have a definite volume. It can take up an entire room, or it can be compressed down into a canister. Liquid has a little bit of compressibility, but not very much. And solids, absolutely not. So you definitely know your solid, liquid, and gas. Solids are the coldest. Gases are the hottest. All right, so related to this, we need to understand the primary idea of chemistry is that you can neither create nor destroy matter. This is called the conservation of the law of conservation of matter. And what that says is, just as I stated, you can't make nor can you destroy anything. It only can just change its shape or form, structure. And so in this example here, you'll see the basics of chemistry. You see on the left, we have methane. It is a natural gas. It's what we use in our cooking, the blue flame of your stoves. It's also what your food breaks down into and becomes as it decomposes. And so we toot it out. If we were to put a fire to it, it would light it in the presence of oxygen and create that blue flame. Well, what you should notice, though, is that the left side produces these gases on the right side, carbon dioxide and water, but they're not even. You'll see there are 4 greens on the left. There's only 2 on the right. So this is not holding true to that law of conservation of matter or conservation of mass. You'll notice there's 4 H's on the left, only 2 on the right. 2 oxygens on the left, 3 on the right. So we got to fix that. And so every single reaction, every single part of chemistry is always going to end up balanced. This is what should be represented. There are 4 oxygens. There is a 2 as a coefficient in front of this oxygen, making that a total of 4. There is 2 of them here, and there are 2 of them here, which gives us 4. There are 2 times 2 for the hydrogen, which is the 4 over here on the right. So everything is balanced with this reaction. Now, if we did this experimentally, what you would see is that if we even sealed the containers, we can prove this even with complex reactions. So in this example, there would be some sodium hydroxide that mixes in with copper sulfate, and it produces a sodium sulfate and a copper hydroxide. But after the reaction, even though the materials look different, even though they have different properties, there will be no change in that weight. That weight started out at 67 grams. It will end at 67 grams. So there is proof that reactions will hold true. All right. Chemical and physical changes. What we need to understand about this is you need to be able to describe what is a physical change, what is a chemical change. There are definitions here. Physical change simply states that there will be no change in its chemical formula. Whereas opposed to a chemical change, well, just by its name implies that there will actually be something that changes. Chemical changes cannot be reversed. Physical changes, generally, there are some exceptions, and physical changes, they can be reversed. If we melt water, we can refreeze it. We can return it, and the chemical formula has not changed. If we chopped wood in half, we could put it back together and it would be whole. There might be a few wood spurs that are missing, a few pieces of sawdust, but by and large, it's all still there. Whenever food rots, there's no way that you can change it and make it edible still. When wood burns, it turns to ash. You cannot change that. When we digest food, well, the byproducts of that, you wouldn't want to go near them for very long. And then the rusting, of course, is the same scenario. If you leave your bike out, it's going to turn into a powder, and there's no going back from that. Now, associated with this is the idea of the properties that are associated, how we can describe and measure those changes. So a chemical property is something that describes how much it's going to change. So the acidity of the compound, how much acid is in there, how much does it dissolve a metal, reactivity, does it cause a big vigorous combustion or something that goes wrong, changes, flammability, does it burn, toxicity, is it something dangerous to us? On the other hand, the physical properties, those are the ones that you use your senses to try and describe the material. What is its color? What is its taste? What does it smell? How big? How heavy? How thick? These are all descriptions, but they don't have anything to do with what their chemical formula is. Now, further, we can classify these properties as either intensive or extensive. And the easy way to remember this is that intensive properties are things that are inside the material and do not change. The boiling point of water, no matter where you go, will not change. The freezing point will not change. The density, which is another word for concentration, those are properties that don't change no matter where you take the substance. If I take gold, it will be a predictable density. If I take the density of water, it will be predictable no matter what. However, extensive properties depend on how much there is. The more I have, the more mass, the more weight. The more I have, the larger the space it's going to fill up, the more volume. So those are very easy distinguishing characteristics between the two. Now, further, let's go and revisit our discussion about matter. Every material on the face of the earth is made up of matter. It's going to either be classified in two different ways. It's either going to be pure or it's going to be a mixture. The pure items are the atoms, molecules, and compounds. Atoms are over on the left. They are single pieces of matter that are elements on the periodic table. We have 118 of them known. They can establish by themselves. In fact, if they do exist by themselves, they're called monatomic, meaning mono, meaning only has one atom. If we talk about molecules, that's where we start combining them together. Now, it's not a mixture because it can stay by itself. So this is whenever we have two or more atoms stuck together. Now, notice in each one of these examples, they're all the same. That's not necessarily always the case. Molecules can be the same, they can be different, but compounds must be different. So we need to be able to distinguish. All compounds are molecules, but not all, I'm sorry, all molecules can be, well, no, we got to get this right. All compounds are molecules, but not all molecules are compounds. I think I said that right. Let's make sure. Everything is a molecule. If you combine them together, everything is a molecule. If it is different, it is a compound. Let's just say it that way and make it simple, and then we won't have the idiot test on me anymore. Now, with these molecules, there is a specific type. I've already mentioned the monatomic, so let's now go into the diatomic. Di means two in this case. So there are 7 particular elements on the periodic table that are very special. They're the only 7 of 118 that can be found in nature, that are found in nature. When they are by themselves, they must be found as a pair. Hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, iodine will never be found by themselves as monatomic. These are the only 7. The way that you can remember these is through a mnemonic device that is called Brinkelhoff. Now, if you want to come up with a different way to try and memorize it, that's perfectly fine, but this seems to be the universal standard for chemistry, is that we combine all of their nuclear symbols into something that kind of spells out something that's pronounceable. So that's a Brinkelhoff. Now, where they are found on the periodic table makes it also a little bit easier. I'm going to cross off one of them. We don't associate astatine with this. So notice 6 of them are all together over here on the right, and it points to the one additional one over here on the left, hydrogen. We will learn why these form diatomic molecules at some point. Not right now. I'm not worried about that. All I'm worried about you doing is being able to remember, to recall what the 7 diatomic elements are. So going back, we have the molecules. They can be the same or they can be different. Compounds must be different. Molecules can be divided into those diatomic or monatomic. So here is the classification of matter. We have the pure substances, which we've just been talking about. Now let's take a little bit of time and let's talk about the mixtures. Mixtures can be classified into one of 2 different ways. There are homogeneous, which means that you cannot distinguish the 2 materials that are together. They are homogeneous. Some other people might pronounce it this way. This is how we talk about our milk. Our milk is homogenized. It has been mixed up so that we don't have a fat, a water, and a cream layer. It's all been mixed together nicely. Homogeneous. Heterogeneous, on the opposite side of that, is though where we can mix things together and they may even temporarily look mixed, but we can still separate them. It's like when you get a pizza. If you don't like the pepperonis, you can peel them off. That is a heterogeneous mixture. As opposed to a milkshake, if you don't like the chocolate, it's stuck in there. There's no way for you to separate that. That's a homogeneous mixture. Reiterating this now with a more atomic scale model. Again, this is what the AP likes for you to be able to draw and be able to distinguish. Heterogeneous this time is on the left, and you notice it is quite easy to separate one material from the other, as opposed to the homogeneous on the right. It is evenly distributed. No matter where I take my sample, I will get an even distribution of the same amounts of the 2 materials. Now, let me take you to one scenario, though, that is a little bit different. There is a true solution, which is homogeneous, where the materials are all mixed together. There is a colloidal solution. And what a colloidal solution is again, just like our milk, the particles are so small that we cannot separate them, even though they may not be completely homogeneous, and over time they may separate. The particles are so small that they actually will just stay suspended in the solution. So colloidal suspensions are solutions, but over time they will settle, but it will take a long time. A suspension will happen quickly. Think about your Italian dressings. If you have oil and vinegar mixed together, you shake it and they will stay mixed for a very short amount of time and then they separate. That is a suspension. And so it is only temporarily homogeneous. More long-term, it stays as a heterogeneous. So this completes our ideas of the classification of matter, where we have pure versus mixtures. The homogeneous and heterogeneous are on the left. We have the compounds, molecules, and elements on the right. The last term I wish to share with you today is about the allotropes. The allotropes are a specific type of compounds, of molecules. And what happens in these is that we have the same elements, but they have different numbers of atoms. The best way to remember these, or the easiest examples to remember these from, is oxygen, which is O2. It will have 2 oxygen atoms versus O3, which is ozone. It will have 3 identical oxygen atoms. Ozone happens in the upper layers of our atmosphere. Whenever we have a lightning strike, it splits the oxygens, and they then combine with some remnant oxygen that's floating around. The oxygen is just abundant in our atmosphere everywhere. We're breathing it. It is 18% of our air. Ozone makes up a very small fraction of our atmosphere. Another one is the diamond, which is a C60 molecule versus a C6 for graphite. Graphite is in our pencils. Diamond is a very hard structure. Diamonds form under immense pressure and heat. So as they are pushed together, those graphite layers start to collapse and they start to combine together and they make larger and larger molecules, which are stable and very, very dense. and we use them for sort of many purposes, industrial as things that we enjoy to give to other folks. All right, this is everything that I wish to share with you. Thank you for staying with me. Hopefully, you're watching this on a speed so that you can get through it a little quicker and get to your homework. Thank you so much. Have a great day, and I will see you very soon. Bye bye.